Hello all. In this video we will be looking at the various aspects related to composites. So, we will start with the different forms in which we can buy or get these fibers, and then what are the different fabrication methods that are available to prepare the composite members or composite structures. Later we will also look at different aspects what a person who is working on composites should be aware of. In addition to knowing about the materials, he should also be knowing about the mechanics, the testing and other aspects which we will look into. And finally, we will see as a person who is looking at the design of composites, there are different levels at which he has to be aware of, or he should be equipped with, so as to be a better designer. So, we will first start with different fibers available. So, the first is a dry fabric. So, here I have 4 different fabrics starting from glass, carbon, Kevlar, and the last one is a hybrid let us say between carbon and Kevlar. So, what I am trying to show you here is dry fabric, as the name says, it is only the fabric meaning only the fibers are there. So, we will use this as a starting material and then add in the liquid resin and later cure it to get to the composites. So, this is where we can start with while preparing these composites, but this is not the only way we start with. There is another category called as pre-preg, where we infuse the resin along with the fabric. So, when we get it or buy it, we get both the resin and the fabric together, but this resin is partially cured, meaning it is not completely cured, but after we get it and we prepare this composite, then we have to again subject it to curing before it turns into a very solid state or strong material. So, meaning that prepregs are useful because it makes the process of preparing these composites much easier, because it has both the fabric as well as the resin together. You do not need to add them together during preparation. And other category is there are some manufacturing methods where you directly start with a spool of the composite fiber. So, we usually call this as tow. Tow means a collection of fibers. Individual fibers, depending on what we are looking at, let us say glass or carbon, are in the order of 10 microns plus or minus. So, these are very small. Usually they are not there individually, they are got together, and what we see is a tow where it is a collection of these individual fibers together. But here what we see is a spool of these let us say here what we see is a glass fiber which is used in some of the fabrication methods. And lastly, we have also discussed about these chopped fibers, where instead of these continuous fibers, all the early ones we have seen, the dry fabric, pre-preg as well as the spool, these are all continuous fibers. But there are some applications where we use chopped fiber, mostly because it is cheap, but still it can give intermediate, or I would say close to good mechanical properties as well. So, having seen these different forms of fibers which are available for us to go ahead with the fabrication, now let us look into the different fabrication methods. Of course, since composite is an evolving field, there are several different methods which are already existing or coming up. We will look at the most commonly used methods. We will start with hand layup. Hand layup is the oldest of the methods, and even now most people rely on hand layup because you do have a lot of control, and this allows you to come up with complex structures as well. So, as shown in this figure, we start with this open mold. So, at the bottom we have a mold. On the surface of the mold you need to apply a release agent, so that after you prepare the composite you can remove it from the mold. But once you have this release agent, and then there is a reinforcement which is between the release agent and the fabric where we are applying. So, on top of it we apply the let us say the dry fabric. So, once we apply the dry fabric, on that we pour the resin. These are done in two ways. One, you have multiple layers of dry fabrics placed and then you pour the resin, or at each layer you pour the resin and then use add the other dry fabric. So, in this way this matrix or the resin helps to bond all these fabrics together, and then you can use a roller to basically squeeze out the extra matrix material. So, probably you might be aware the strength or the mechanical properties are coming from the fabric or the fiber. So, we need to ensure the matrix is there just to bond or bring these fibers together. So, we need to squeeze out as much of matrix out such that you have a high fraction of fibers, because fibers are the ones which bring the strength to the material. But another aspect you need to consider is the bonding between the matrix and the fiber is also important. So, sometimes there are some coatings which are applied on the fibers so that it allows for a proper bonding between the matrix and the fiber. So, as we already mentioned, this is a manual laying procedure. So, of course, it takes a long time, it is a manual labor intensive process. But after we lay the fabrics and pour the resin and then squeeze it out using the roller, that is when we need to cure it. There are several ways of curing it. One is room temperature curing, meaning once you apply the resin and then leave it for let us say one full day, the curing happens at room temperature and at normal pressure. But usually in industry people use autoclaves to cure. So, autoclave is a closed vessel where it maintains both pressure and temperature. So, in this figure you can see this is the autoclave and this is the structure that is being prepared in this autoclave. Of course, what you see here is a very industrial size or a very big autoclave where a big structure could be prepared all in one go. But usually in the laboratory autoclaves, these are more compact, so that these are limited or restricted to preparing smaller components of composites. So, the way to go is first we do the hand layer meaning we lay these fabrics or the prepregs, and then for the final curing we put it in this autoclave where it is subjected to high pressures and temperatures. The reason why we have high temperatures is this speeds up the curing, so that in a reasonable amount of time or a short durations of time we can get these cured composites. And pressures are used so that this squeezing of this matrix, the extra matrix in this mixture of matrix and the fabrics will be done by applying the pressure. This ensures that we get very high fractions of fibers, or the fiber volume fractions are high with respect to autoclave. That is the reason why for high performance composites especially they go with autoclave. But if there is no autoclave facility, the other alternative is to keep it in a oven where you only control the temperature if not the pressure. So, the next fabrication method we look at is the filament winding. So, this is an automated process, and for this we rely on a flexible fiber. So, if you are looking at this figure, we will start with this continuous strand rowing or the tow or this collection of fibers together. So, these fibers are then passed through a resin bath. So, when they pass through the resin bath, these fibers are now wet. So, these wetted fibers are wound on a rotating mandrel. So, this is the mandrel we are looking at. So, let us say if this is rotating, basically it is trying to pull the fibers onto the mandrel. So, these are used for several applications such as pressure vessels and these rocket motor casings. And the good thing about the advantage of using filament winding is you can control the winding angle. So, for example, this angle can be controlled or the gap between two fiber layups can be controlled. So, this is a very automated process where there are many process variables one can optimize to get the optimum structure we are looking at. So, the next method again we look at is pultrusion. Pultrusion again we start with like rovings or the tows or the spool of fibers. So, this is the fiber. So, this is passed through a resin bath. So, basically we are wetting these fibers and then they are passed through formers or dies. Basically they are trying to compact these fibers together to give it a final shape, and in this die it can also apply the pressures and the temperatures, so as it helps in curing of these composites. So, these rollers here they apply the pull forces on the finished product. So, at the end what we get is a pultruded product. So, this is a very cost effective process, that is the reason why this is used in the industry. So, this is suitable for prismatic products such as the beams, it can be I beam or a T beam, and then the channels as well as hollow tubes. And the advantage of this process is when it is being pulled, it can be cut to the final desired shape. So, it has a good surface finish as well as it can be cut to the required shape during the manufacturing process itself. So, next we move to braiding. This is another way of weaving of these composites, where as you can see here it is not just two strands, but there are several strands which are interlaced fibers. So, because we are interlacing these fibers, we can achieve these complex shapes. This is again an automated process, therefore, it is more cost effective. And the kind of products we prepare include the ropes, tubes, beams and strips. Essentially, it is helpful to prepare slender members or to prepare these hollow tubes or hollow vessels as well. So, lastly we will be looking at this resin transfer molding, which we call it as RTM method, where we have this bottom mold. In the mold you first place the fabric. Once the fabric is placed, on top of it you cover it with a vacuum bag. So, essentially what we have is this fabric is sitting in between the vacuum bag and the mold, and then we pump out the air to create vacuum. So, essentially we create a vacuum. Because of this vacuum, from here this is the resin reservoir from which the resin passes through and enters the mold. So, once it enters the mold, it wets the fabric and then later it can be cured to give a proper shape. This actually is also called as vacuum assisted RTM or the resin transfer method. So, because here we are using resin, but there is another way of preparing it. We will follow the same procedure, but instead of vacuum, the high pressures can be applied to get the final shapes. So, what we have briefly seen are the various methods by which we can prepare these composites. Of course, when we go to the industry, there are much more sophisticated methods or a combination of few of the methods we have already discussed. Now, we will move into looking at different aspects one need to know working with composites. You might be a manufacturer in the composites or an analyst or a designer, or maybe working with the finished products of composites itself. But let us see what are the different knowledge on composites one need to know, so that you are on top of the things or you have a better idea about how this is prepared or how it behaves or how where it can be used. First, one needs to know a bit about the material science, starting from fibers, matrix materials, and also the interface between the fiber and the matrix, because as we mentioned just a few minutes back, saying that the interface also plays a big role, because once we have a good bond between the matrix and fiber, it can transfer the load. The fibers take the load, but the matrix load transfer can be good. But if this interface is poor, again it leads to defects, and then the overall performance of the composite component or structure is decreased. One should also be aware of the different fabrication methods available. This will help to pick the appropriate fabrication method for the desired application, which could either reduce the cost as well as to get a high quality product which meets the function requirements. Analysis is another important step where once a design is finalized, we need to ensure that the particular design is safe. So, one can do analysis at multiple levels, starting with just the material itself to see what are the properties or what are the effective properties of the composite material. But later he might be also be interested to see, once this material used in a structure, what is the structural analysis of it, meaning that for a given load, what are the kinds of deflections or the stresses which are induced in the material, that will give an idea about how it meets the requirements or whether it fails or not. And design is another aspect which is very different compared to the same component design using metals, because now since we are using composites which are not isotropic, because aluminum and steel are isotropic, meaning it will have the same properties in any direction. But composites, we will look at it more in the next week, but they are anisotropic, meaning their properties are high along the direction of the fibers, but transfers to the fibers their performance might be less. So, we need to know how to design in such a way that we take advantage of these directional properties of the composites. And from going from the materials to the structure, again there are some design principles one need to follow or one need to be aware of, so as to arrive at a more optimal designs. And finally, testing. So, once we either prepare the structure or even before we prepare the structure, once we narrow down on the material, we need to know what are the effective properties of these materials. So, for that, either one can get these data from manufacturer or from literature, but it is always good to do the testing in house, because the same material, the properties can vary based on the manufacturing methods used or even the batch from which these materials are prepared. So, it is always good to have a testing in the place where it is fabricated itself. But the point I am trying to make here is, we cannot again go with the standard test methods available for metals, because again as we mentioned, composites have directional properties. So, the kind of test we do should be specific to these composites, and again the failure mechanisms involved when we were either testing till failure will be very different. That is why one needs to know the fatigue or failure behavior of these materials. Lastly, since we are looking at a complete life of a product, it is not just a matter of fabricating it or knowing how to design or analyze, but we should also be aware that we should meet these for long periods of time. So, then we need to ensure that the structure is intact. How do we ensure? We either do some inspections. This could be either destructive or non-destructive, and once we find a defect, then we need to either see whether we have to discard the material completely or whether it can be repaired. So, there are several options available by which we can repair the composite. So, being aware of it will put you in a better position to choose the way ahead after we find the defects. So, because often what happens is once the repair is done at the right time and in a proper way, that can take care till the end of the service life. So, this should give you a sense of what are the kind of informations one should be aware of, so that while they are working with these composites, they are well prepared or more aware of how to look into the various aspects of these composites and to ensure that the product is servicing well, not just at the beginning, but towards the entire lifetime. Lastly, I also want to stress about the designing with composites, because here we see this is where it is very different from designing with metals. So, let us start with a lamina. So, now the question to be asked is there any design involved in picking up a lamina? The answer is yes, because now one can say they have picked a particular fiber and a particular matrix. But now the design can be like, what is the volume fraction we want with the fiber, such that these materials are suitable for this particular application. Of course, the higher is the volume fraction, the better it is, but then it has it has to compensate for the cost, because the cost increases if you are looking at very high volume fractions. So, how do we get the properties of these lamina? Of course, one can go ahead and test it, but not every time we go with testing. Sometimes we also need to estimate what are the effective properties. Let us say you know the properties of the fibers, as well as you know the properties of the matrix. Can we use this information along with the volume fraction of these fibers to predict what are the properties of the lamina? That is what we will call it as micromechanics of lamina, which we will be studying in the next few weeks. So, that is all the design and analysis involved while we are looking at just a single layer, which we now call it as the lamina or the ply. Then from lamina we go to a laminate, where we stack up individual layers to create a laminate. So, in practice these layers can go as much as 30 or 40 in several industries. But when we are designing these laminates, we have few design options. First, we need to choose whether we are using the same lamina or we are mixing different laminas, which is possible, because in reality it is not just the composites which form the laminate, because sometimes it could be a composite and then you might also have a metallic sheet like an aluminum sheet or a titanium sheet, but some of the other layers could be composites. And then each of these sheets or the layers will have their own thickness. So, one can decide as a designer what is the thickness of each of these layers. But after this there are few more important design options, like what is the orientation, because these fibers are directional. You can either have a 0 degrees, 90 degrees or some incline between 0 and 90. So, that is called the orientation of each. And then what also matters is the sequence, or the stacking sequence is what we call it. So, whether the first layer will be 0 and then going to the second layer, what is the orientation. So, this stacking sequence is also something a designer have to come up with to meet the particular requirement, because depending on some structures might only have a longitudinal load or a in plane load, but other structures might have a torsional loads. Depending on whether it is a torsional load or an in plane load or a bending load, the stacking sequences can be optimized for these specific loading scenarios. But what I am trying to make come now is this process of going from the lamina to the laminate is what we call it still as the design of material. So, laminate is not the structure, because this is again the building block before we go to the final structure. So, going from the lamina to the laminate is still we are in the process of designing the material. This is how it is different from the design of metals, because once I take aluminum, right, aluminum is just one metal, there is nothing, there is no scope for me to change the properties, but I can always change the shape or the size of these aluminum to get to the structure. So, similarly in composites, once we have these laminate, then we go to the structure. Let us say we are designing this wing of an aeroplane. Then the designer should come up with what is the optimum shape or the size of these laminate, so as to have a better superior aerodynamic performance as well as the structural integrity is maintained. So, this we call it as the design of the structure. So, again I will try to go into the details about what are the different aspects involved in the designing of the composites. So, first one should be aware of the mechanics both at the laminar level as well as the laminate level, meaning once I know the individual properties of fiber and matrix, can I predict what is the properties of the lamina, or once I know that there are these n number of laminas each with a particular orientation, then coming to the laminate, what are its effective properties, what is the stiffness of these lamina or the failure resistance of these laminate. Then we also are interested in the failure behavior of these lamina and laminates. So, again like we have failure theories for metals, like that we have failure criteria one can apply to see for a given loading scenario whether these lamina will fail or not. Similarly, that same knowledge can be taken from the lamina to the laminate, because when we go to the laminate, in addition to failure in lamina, this can also fail in other ways, something like delamination, meaning like there could be failures between these two layers, because between these two layers we do not have much of the fiber, and what we have is the matrix material which is considered to be weak. So, delamination is a very critical failure mechanism, because this most often becomes the weakest link. So, one need to be aware of these failure criteria as well as the failure mechanism, so as to know what are the limits we can take this composite till, or what are the stresses at which we should limit our design to. Later we also need to know several design considerations which are more specific to composites. Like I already mentioned, saying that if the loads are twist versus bending, then there are some considerations saying what should be your top layer, whether it should be a 0° or a 45° to take care of these loads. But in addition to that, we also need to take care of what are the temperature effects. So, when there is a change in the temperature, what are the thermal stresses built up in the composite. And similarly, we can also mention about humidity effects, because especially polymer matrix composites, right, when they are exposed to humidity, they absorb moisture. When they absorb moisture, they expand or swell. Because of this swelling, again there are some stresses induced in this composite. So, all these aspects has to be taken care of, so as to know what are the maximum stresses we can expect in this structure. That should help you to come up with a better design. And finally, it is not just one single structure we prepare with a composite, right. Usually these are multiple components which has to be joined. So, even in composites, it could be you are joining a composite with a metal, or a composite with a ceramic, or maybe two composites itself. So, these joints, again there are several different joining methods available. The most common is the bonded joints, where you again use a polymer resin to join these two components. But in addition to bonding, they are again like riveted joints or even bolted joints people use, so as to reinforce or give an additional safety to the composite structure. And repairs also involves a design, meaning like say to the wing of the structure someone notices a defect on the surface. Then one could say, okay, instead of replacing the whole wing, we will only patch it up, meaning we will stick a patch of composite on that place. Then the design aspects involved are how many layers should we have such that this particular defect is protected, and what are the dimensions of this patch such that we are not compromising neither the wing or exposing it to any future failures. So, these are the different aspects, the design aspects one need to be aware of if somebody is aspiring to become a composites designer. So, now let us summarize what we have discussed in this video. First, we started with the fiber forms, saying that these are available either as dry fabrics, as prepregs, where we have both the fibers as well as the partially cued matrix, or we can have it as spool in terms of tau, which is a bundle of fibers, or we can also have these chopped fibers. And later we discussed about different manufacturing methods or the fabrication methods. We started with hand layup, which is manually intensive. Later these hand layup things can either be cured in an oven or an autoclave. We said autoclave is a vessel where we can go for high temperatures and pressures, and usually these are used when we are looking at very superior performances, because this helps us to achieve high volume fractions. And we also looked at these filament winding, pultrusion, braiding. These are the different methods where we can start with a spool of a fiber to come to composite structures. And lastly, we also looked at this resin transfer molding, we call it as RTM, but most common of these is the vacuum assisted resin transfer molding, where we use vacuum to infuse the epoxy or the resin into the fabric material. Finally, we looked at various aspects of the composites involved, saying that we should be aware of the material science of these fibers and the matrix as well as that their interfaces. We should also be aware of the mechanics of how these fibers or the lamina or the laminae work, and then various design considerations one should be looking at while we are looking at these composites. And later we also said the maintenance as well as repairs, these are considerations one should be aware of or should be knowing to come up with a better composite structure or a product. So, with this we will conclude the first week, where we have discussed about the introduction to the composite. Of course, as you have seen, we did not have time to cover up all the aspects, because composites is a very vast subject. Actually, even talking about fabrication methods of composites itself is a course by itself. But since we are more focused on all aspects of the composites, we try to finish up in a week the introduction to the composites. But in the following weeks, we will be looking at the mechanics of the composite, starting with mechanics at the laminar level, and later we will go it at the laminate level. Before finally, we will also look at various design aspects of the composites before we conclude this part on the composites. Thank you then, see you later.